Welcome to my channel and thanks for stopping by. In my previous video, I discussed in details the concept of Mann-Whitney test. So in today's video, I'll be demonstrating how to perform and interpret the Kruskal-Wallis H test in SPSS. My name is Titocan and this is Titocan Solutions, a YouTube channel for improving the knowledge of how to do things. But before I go into the demonstrations, let me quickly give you the synopsis. The Kruskal-Wallis H test is a non-parametric test used to determine if there are statistically significant differences between the distributions of three or more independent groups on a continuous or ordinal variable. It is an extension of the Mann-Whitney test to more than two groups. Kruskal-Wallis H test is used as an alternative to one-way ANOVA, especially when the assumptions of normality and homogeneity of variance are violated. This means it is also important that you know what analysis of variance or ANOVA is, especially the parametric assumptions of ANOVA, so that it will be more comprehensive to you the reason for the alternative choice. To learn more about ANOVA, please see my video on analysis of variance in SPSS, effect size and interpretations. Now, the Kruskal-Wallis H test ranks the data from all groups together and compares the rank sum between the groups. It does not require the assumptions that the data should be normally distributed, making it a robust test for non-parametric data. As key features, the dependent variable should be ordinal scale or continuous scale. The independent variable should be categorical with three or more groups. Please listen again. The independent variable should be categorical with three or more groups. That is, the group of the independent variable must be more than two. The following are the conditions that will make Kruskal-Wallis H test suitable for your data. 1. Presence of non-normal data. That is, if the dependent variable is not normally distributed across groups. 2. Presence of ordinal data. That is, if the dependent variables are measured on ordinal scales. 3. Heterogeneous variance. That is, if the variances between groups are not equal, or if the assumption of homogeneity of variances is violated. 4. Presence of outliers. That is, if the dependent variables consist of extreme values or unnecessarily large value that can have implications on the mean. And 5. Unequal group sizes. That is, if the dependent variables have unequal sample sizes. In other words, Kruskal-Wallis H test can handle unequal sample sizes between groups, making it flexible for real-world data scenario. Now, let's go into SPSS and take a look at the dataset for this demonstration. This table of data is fictitious, but represents the performance of students in an impromptu class test in 3 subjects. The independent variable is the subject, comprising of mathematics, English, and physics, while the dependent variable is the test scores. As you can see, the independent variable has 3 groups, and the dependent variable is a continuous scale variable. So we can use the Kruskal-Wallis H test to determine if there are significant differences in the group of scores across the 3 subjects or groups. So the null and alternate hypothesis will be as follows. Null hypothesis states that the distribution of scores is the same across categories of subjects, while the alternative hypothesis states that the distribution of scores is not the same across categories of subjects. That is, at least, the distribution of one subject is different from the others. However, before you can proceed to perform this non-parametric test, let's quickly verify that the test of normality and homogeneity of variances are violated by the data, which are the most required conditions necessary to perform Kruskal-Wallis H test. To do that, you will have to first of all split the independent variable into groups according to the subjects in this case, and thereafter perform a frequency curve distribution on the dependent variable. Now, go to the menu bar and click on Data. From the submenu, click on Split File to open the Split File dialog box. In this dialog box, you have your variables in the box on the left. Now, click the radio button for Compare Means to activate the column for Group Based On. Then click on your independent variable subject and then click on this transfer arrow key to move it to the group based on bus. Then click OK to close this dialog box. Behind the scene, the dependent variable has been splitted between the three groups or subjects. Again, go to the menu bar and click on Analyze. From the sub-menu, click on Descriptive Statistics, and from the drop-down options, click on Frequencies to open the Frequencies dialog box as you can see. Now click on your dependent variable, test scores, and then click on this transfer arrow key to move it to the variables box. Go straight to Chart button and click to open it. In this dialog box, click the radio button for histograms and then check the box for Show Normal Curve on Histogram. Click Continue to close this dialog box. Uncheck the box for Display Frequency Tables. And finally, click on OK to produce the plots. Now, the histograms and the curve distributions for the subjects have been produced. And as you can see, the distribution for mathematics, English, and physics are skewed, meaning they are not normally distributed. Therefore, the test of normality has been violated by this data and as a result qualifies the choice to perform Kruskal-Wallis H test. Now, let's check if the homogeneity of variances is also violated by this dataset. To do that, we are going to pretend as if we are performing analysis of variance. But remember that we had splitted the dependent variable across the groups before we performed the frequency distribution. So, we will return to unsplit the dependent variable before we can test for the homogeneity of variances. To do that, go to the menu bar and click on Data. From the sub-menu, click on Split File to open the Split File dialog box. In this dialog box, your settings are still intact. Now, click the radio button for Analyze All Cases. Do not create groups to gray out the column and cancel whatever split that was done. Then click OK to close this dialog box. Behind the scene, the dependent variable has been unsplitted among the three groups. Now, let's test for homogeneity of variances. To do that, go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Compare Means. And from the drop-down options, click on One-Way ANOVA. In the dialog box that opens, click on your dependent variable scores and click on this transfer arrow key to transfer it to the dependent list box on the right. Then, click on your independent variable subject and click on this transfer arrow key to move it to the factor box. Since we are only interested in the homogeneity of variances, go straight and click on the Options button to open the Options dialog box. Then, check the box for Homogeneity of Variance Test, and then click Continue to close this dialog box. Thereafter, click OK to produce the results for Homogeneity of Variance Test. As you can see, the tests of homogeneity of variances have been produced for Levin statistics. If the p-value designated as Xig is greater than 0.05, then the test of homogeneity of variances is not violated, meaning that there is equal variance across the groups. But if the p-value designated as Xig is less than 0.05, then the test of homogeneity of variances is violated, meaning that there is no equal variances across the groups. As you can see, the p-value is 0.041, which is less than 0.05, and this indicates that the assumption of homogeneity of variances is violated or not met, meaning there is no equal variance across the subjects or groups. These two tests evidently qualify the application of Kruskal-Wallis H test to analyze this dataset. So at this point, we can go ahead to perform Kruskal-Wallis H test. However, there are two different routes or pathways to follow to perform Kruskal-Wallis H test. Route 1 is the independent samples option, and Route 2 is the legacy dialogues option. However, whichever route you choose to follow will produce the same results, except Route 1, which has the features necessary to help determine a pairwise comparisons, especially if there are significant differences among the categories of your independent variable. This feature is what makes the Route 1 a more preferred pathway to me, and I will always encourage you to follow this route. But in this video, I will concentrate more on the Route 1, and thereafter quickly demonstrate the Route 2. Now, let's explore Route 1. The Route 1 is the independent samples option. To follow this route, go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Non-parametric tests, and from the drop-down options, click on Independent Samples to open the dialog box. In this dialog box, there are 3 pages, such as Objectives, Fields, and Settings, as you can see. In the Objective page, leave the radio button for the default selection unchanged. If the radio button for automatically compare distributions across group is not selected by default, please kindly select it now, as the options required for this analysis. Then, click to open the Fields page. In this Fields page, click the radio button for Use Custom Fields assignment. Then go to your variables in the box on the left, click on the dependent variable scores, and click on this transfer arrow key to move it to the test fields. Thereafter, click on the independent variable subject and click on the transfer arrow key to move it to the group column. Then, click to open the settings page. In this page, the Choose Test options is opened by default. Here, click on the radio button for Customize Test to activate the boxes for non-parametric tests. Now, since our interest is to perform Kruskal-Wallis H test, go ahead and check the box for Kruskal-Wallis one-way and ANOVA case samples, and ensure that the multiple comparison is set for all pairwise. Then, click on Test Options and ensure that the significance level is set at 0.05 and the confidence interval is set at 95%. If there are missing values in your dataset, then use the Exclude Cases options to fix your missing values. But since my data for these demonstrations does not have any missing values, I will just go ahead and click Run to perform the Kruskal-Wallis H test and produce the results in the output window. As you can see, the Kruskal-Wallis H test results have been produced and provided in the hypothesis test summary table. This table is a simplified tabular form consisting of the null hypothesis column, the test column, the p-value column designated as SIG, and the decision column. From this table, you can easily decide whether to accept or reject the null hypothesis according to the provision of the p-value as one of the determinant factors. Basically, if the p-value designated as SIG is less than 0.05, it indicates that there are significant differences. But if the p-value is greater than 0.05, then there are no significant differences. As you can see from this table, the p-value is 0.012, and this is of course less than 0.05, indicating that there are statistically significant differences among the scores across categories of subjects. Hence, the decision will be to reject the null hypothesis. As a result, there is a need to find out where the differences which are statistically significant are coming from among the categories of subjects. One of the best ways to ascertain this is to conduct a pairwise comparisons among the subjects. To do that, double-click on this table to open the Model Viewer interface, where you can quickly and easily perform the pairwise comparisons. In this Model Viewer, there are 2 view sections. The section on the left-hand side is the main view, and it contains the hypothesis test summary table, which you have seen earlier, while the section on the right-hand side is the auxiliary view, which contains the independent samples Kruskal-Wallis test in a box plot and table. This section also contains the view drop-down option, where you can activate the Kruskal-Wallis system to perform different statistical events, including the pairwise comparisons. Here, the box plot shows that the independent variable subjects such as the mathematics, the English, and the physics are truly not normally distributed, evidently seen from the unequal sizes of the individual box and unequal length of their whiskers. The plot also shows the presence of 2 outliers in mathematics. This is the more reason Kruskal-Wallis H test is a more robust test and therefore is used to analyze this set of data that violate the parametric assumptions of ANOVA. Moving forward, this table shows that there are 54 students who participated in the impromptu class test. The chi-square test statistics result is 8.792. The degrees of freedom is 2, and the p-value designated as asymptotic SIG two-state test is 0.012, which is the same numeric p-value in the table on the left-hand side. To obtain the numeric values of the mean ranks of the subjects, please put your cursor on the horizontal line on each of the boxes in the box plot. Please note that you are expected to represent all the numeric values in the body of your report or thesis. So you may have to copy out the mean ranks values as you put your cursor on the horizontal lines in each of the bars in the box plot. Now, let's perform the pairwise comparisons. To do that, click on the drop-down view button to project the different statistical events. Go down the options and click on pairwise comparisons. And immediately, the pairwise comparisons results, such as the script plot and the table of the pairwise comparisons, are produced. As you can see from the script plot and the table, the statistically significant differences are found to be coming from the pair of mathematics and physics, identified in their yellow color. This clear identification is one of the features that made this Route 1 pathway to be more appealing to follow to perform the Kruskal-Wallis H test. In case you wish to obtain the feed information of the dependent variable comprising of the basic descriptive statistics, go to the View drop-down button again and click the option for Continuous Feed Information. A histogram plot containing the basic descriptive statistics numeric values will be produced, showing the frequency of the scores and the basic descriptive statistics. If you are interested in copying the tables and plots in either the main view section or in the auxiliary view section, it is possible. How do we do this? Let me show you. Just go to the menu bar and click on Edit. And from the drop-down options, click on Copy Main View to copy whatever is on the main view section, or click on Copy Auxiliary View to copy whatever is on the auxiliary view section. Open a Word document and paste your copied items. Just like that, you have copied what you need to copy. Now that we are done here, go to the menu bar and click on File. From the drop-down options, click on Close to close this model viewer interface. Now, let me quickly take you through the Route 2 pathway. Route 2 is the Legacy Dialogues option. To follow this route, go to the menu bar and click on Analyze. From the submenu, put your cursor on Non-parametric test, and from the drop-down options, put your cursor on Legacy Dialogues. And from the drop-down options, click on K-independent samples to open the dialog box. From the box on the left, click on your dependent variable scores, and click on this transfer arrow key to move it to the test variable list box on the right. Then click on the independent variable subject and click on this transfer arrow key to move it to the grouping variables box. As you can see, there are two question marks in parentheses attached to the independent variable. These question marks are asking you to provide the coding system for the three groups, such as 1 for mathematics, 2 for English, and 3 for physics. So click on the Define Range button, and in the dialog box that opens, enter 1 in the box for minimum range and enter 3 in the box for maximum range, and then click Continue to close this dialog box. As you can now see, the question marks are now replaced by the 1 and 3 coding system that you have just entered. Now, click on the Exact button to open the dialog box. In this dialog box, ensure that the radio button for asymptotic only is checked. Then click Continue to close this dialog box. Now, click the Options button to open the dialog box. Check the box for descriptive, and this will produce the descriptive statistics of the dependent variable. If your data contains missing values or missing data, then under the Missing Values section, you can choose one of the radio buttons to fix the missing value in your dataset. But since the data I am using for this demonstration does not have any missing values, I will just go ahead and click Continue to close this dialog box. Now, under the Test type, ensure that the Kruskal-Wallis H Test box is checked. If in your SPSS package, this box is not checked by default, please kindly check it now since you are performing Kruskal-Wallis H Test. Then click OK for the configurations to process and produce the results of Kruskal-Wallis H test in the output window. Now, the results have been produced, and as you can see, the numeric values in each of the tables here are the same as we had seen when we followed the Route 1 to perform the Kruskal-Wallis H test. This suffices to mean that you can use the route that is more suitable for you. This is how to perform Kruskal-Wallis H test in SPSS, and I hope you'll be able to replicate the non-parametric test procedures to analyze your own dataset and interpret the results. But right now, we have come to the end of this video. If you like this video and you want to see more video contents like this, please like this video by giving it a thumbs up, share this video, and subscribe to my YouTube channel to receive notification every time I publish new and useful contents. Subscription is free. Thanks for your time and subscription. Thanks for liking this video, and I hope to see you again in my next video. Bye.